Now, this is the KF4. It's going to be presented by me. I am Indiana Hoosier. Now, the first thing I'm going to say is the signal right here is going to be a voice, which is going to be sent through an amplifier, which is then going to be mixed with a mixer with this carrier frequency, which is then sent through another amplifier, which is then cleaned up with a bandpass filter, and then finally sent out the antenna. Now, for the first class, it's going to be ECE 312. Now, right here is a mixer. This is what's happening in the waves. X1 of t is equal to a voice signal, x2 of t is equal to my carrier signal. Now, cosine of omega t can also be split up into this right here. Two complex exponentials, e to the j omega t plus e to the negative j omega t divided by 2. Now, because you can factor in this x1 into both of those, you can look over here and see that x1 of t e to the negative j omega t is a phase shift in the frequency domain. So it's x1 of s minus j omega. Now, in the frequency domain, you're going to have the same signal, but it's going to be split and moved into two different spots. Now, we know that a mixer is nonlinear for a couple of reasons. One, because multiplication is a nonlinear function. And we don't want this because we're mixing it with a cosine, and this cosine we do not want to be what's coming out. So this is actually very good. Now, if you look at this, my picture is kind of cutting off this side, but you can see over here that this is what's happening. This is my original frequency, x1 of j omega. Now, this is my y of j omega, and it is moved over to the left-hand side, negative omega naught, which is from my carrier frequency, and then this 10k is actually this limit. It's my frequency of my original x of j omega. Now, filters is the next thing. This first one is a low-pass filter. On the left-hand side, you can see it's t is equal to 0.01 and t is equal to 0.1. They do look very similar to each other. They are slightly different. The only difference for the most part is that their poles are at different places. And because this is a low-pass filter, this magnitude right here starts at 0 and then drops off. A low-pass filter is only letting low frequencies pass through. It is cutting off any high frequencies that are being sent by. Now, this is a high-pass filter. It does the complete opposite. It only lets through high frequencies and cuts off low frequencies. Now, when you combine the two together, you get this bandpass filter. Now, a bandpass filter is a high-pass filter and a low-pass filter multiplied together. And this is only allowing a certain set of frequencies head through there. This one is a little rounded, so you will get some more harmonics and other noise that you don't want to go in there, but it's still pretty much the same idea, because on this left side you're cutting off, you're cutting off on this left side and you're cutting off on this right side, so it is only letting the specific amount that you want to pass through. Now, the next thing is 332. The same circuit from earlier, it's the cell phone, and it's good to know what the signals go through here, but it's also good to know what the actual elements do. These amps in here are usually from common source amplifiers, and here is kind of what is being shown. This is the mixer, this first half right here. VC is going to be my carrier signal, VO is my voice signal, and then VQ is my bias. The bias is pretty much just keeping this transistor over on this part from going into saturation, and there is a capacitor at each of these ends. This is allowing only the current to head this way and straight to the transistor. Now, if there wasn't any, there could be some current that looped back around. We do not want that to happen. And because capacitors act as a short at high frequency, this is really good. By setting these capacitors at a specific frequency, it acts as just going one way. Now, for the bandpass filter that was up to the top, this is just a simple one. It's not exactly what we would normally put down, but it's an LRC circuit. A capacitor acts as a short at high frequency, inductor acts as a short at low frequency. So, by doing so, it acts just as what I talked before. At high frequencies and low frequencies, they're going to be shorted out. Now, when you have the resonant frequency, which is FO is equal to 1 over the square root of LC, that's going to be right here. That's at your peak where you're going to have the most current flowing through there, because both of them are acting more properly and neither one is shorted. Now, the last thing is 342. Now, the main thing in 342 that we talked about is this antenna. An antenna is usually going to be the biggest part in your circuit because you can't necessarily shrink it down. That is because it needs to be able to receive the entire wave. A lot of times you can shrink it a little bit by having a quarter wave or a half wave or something of the sort. Now, it's going to also be sending out at a certain frequency, and when you have a carrier and they say the new 5G network, that's because they've moved up to a 5 gigahertz network. That is the frequency in which they're being sent out to. Now, talked earlier about with this shift right here, that's also what this antenna is going to be using, because it's going to be shifted out there, and at the 5 gigahertz you're going to have a filter out there that is cutting it off right here and right here, so that only your signal is being sent through there, so that way you don't actually listen into the person sitting next to you, their cell phone conversation, and vice versa. So the filters work out there, and the antennas are sending out at just the right frequency so that it'll work properly. Now, for a recap, this is simply the frequency waves just going through the whole circuit. This is your start, this is your carrier wave, and so you're going to start out here. It's going to go through an amplifier at first, which is going to amplify this amplitude because you want it to work properly when you go through the mixer. Now, when you send it through the mixer, it's going to be a phase shift right here and right here, both in the frequency domain. It's just moved over by omega and negative omega naught. That is the frequency of your carrier, your cosine. Now, afterwards, you're going to need to send it through another amplifier. For one, because when you did this phase shift right here, it was cut in half because of the 1/2. So now this amplitude is higher, and it also works now a lot better because this new amplitude, it's going to be filtered out through the bandpass, but when you send it out through the antenna, it's more power that will be sent out there. As I said down here, when it's sent out there, you have a different signal that'll come in the antenna after you've already sent it out to your it's sent to your tower, and the tower knows exactly what to use. I hope you liked my presentation.